Welcome to the day 4 of this workshop on geometric algorithms. So on day 3, that is yesterday, we started talking about covering problems, but on the second half of the session, the participation had dropped significantly. So I thought that in the lack of feedback, affirmative feedback, I will do the second part today. So I'm going to do the second part of covering algorithms today, and then we will move to visibility algorithms. So both things we're going to do today. Okay. So let me. You're not able to see the full screen, right? So far.
Yes, it is visible.
Not the full screen. Here now it's
Okay, so we are going to talk about geometry covering algorithms in this presentation. So the first question is, why are we interested in covering? So covering problems are everywhere in our day-to-day lives. So that is the primary reason. And secondary reason is, I won't say secondary, but it is one of the reasons that the covering problems reveal the elegance of minimalism in geometry. So let's start with a real life example. So let us say you are one of the officials of the Indian government, and you are in a high-powered committee to set up vaccination centers across the country so that every citizen gets access to at least one of the vaccination centers. So obviously, one of the goals that you will have in mind is how to minimize the number of vaccination centers while also providing the service to every citizen. So you would probably like to have more centers in densely populated states and less centers in sparsely populated states, and you would have to do finer refinements when you go to district level, village level, and all these things you have to do. So you have to take into account many factors like population density, geography, cultural factors, and many other things. But you have to do covering, and one of the goals would be definitely to minimize the number of vaccination centers that you are going to set. So this is one of the examples where covering is a real life problem which we want to solve. So let's look at a concrete question first. So this I talked yesterday also, but this I'm repeating today. So suppose you have a city and there are, let's take the pointer. So there are some inhabitants in the city, and some of the places in the city are high density. So for example, this building may require a lot of bandwidth because a lot of mobile devices are probably in this building in this part of the city, whereas this part of the city is less populated and there are less mobile devices. So there is a density pattern across the city. So you want to put base stations or antennas in the city, in certain points of the city, such that all the residents of the city receive coverage from at least one of the antennas. So observe that these antennas have a limited range of service. So an antenna, let us say, can cover only, let us say, up to 100-meter radius. So you have to make sure that you do not count coverage from an antenna which is more than 100 meters away from one of the users. Okay. So for example, in this picture, let us say if somebody is living in this part of the city, he is not getting active coverage from any of the antennas. So we don't want a situation like this. So we want coverage across all the densely populated places at least. Okay. So while minimizing the number of antennas that you must put, so your objective is to put as few antennas as possible such that everybody in the city gets wireless coverage. So how to formulate this problem geometrically? So let us say these points are representative of highly populated, highly dense areas of the city. So points correspond to potential customer location. And the circles correspond to the coverage area of placed antennas. So it means if you place an antenna at this point where I'm pointing, then with this point as the center, up to some radius, you will be able to provide coverage. So every antenna, let us say, has circular coverage. Okay, so this is one of the idealistic assumptions. So for example, in this figure, if you put antennas at the centers of these three yellow circles, then you will be able to provide coverage to each of the potential high density customer locations. So the goal is again to minimize the number of unit radius circles that cover all the given points. So I'm saying unit radius, but it is just for the sake of concreteness. The idea is the circle should be of equal radius. Now you can always scale things up and you can say instead of 1 it is 100 or instead of 1 it is 2 kilometers. You can do such things. But a solution with unit circles will extend naturally to the setting where there are larger circles, but the circles are equal in size. Okay. So any question, any doubts about what is the goal of the problem?
Is there anything, something like the intensity of the coverage here, like the points which are closer to the center or the points which are closer to the periphery?
Okay. So no, so we'll have an assumption that within the circle, the quality of service remains the same. So somebody which is near to the center and somebody which is near to the periphery are getting satisfactory coverage.
Okay.
You have a question, Ahmad? Ahmad, do you want to say something? If not, please mute yourself.
Yeah, sorry.
Okay, thank you. Okay, so we are ready with the question. So now we have to think about the solution, that what should we do in this scenario? So let me tell you that it is one of the most studied problems in geometric covering. And there is a series of work on this problem of covering points with unit circles. And to Wardo, it's already an NP-hard problem. It is known to be an NP-hard problem, and we can only hope for some approximate solutions. So finding an exact solution, the exact minimum number of circles to cover endpoints, that is already shown to be NP-hard. That means a polynomial time solution is not expected.
So is there any formal name to this problem which has been proved as NP-hard?
Yes, it's a geometric set covering with unit disks.
Okay.
And we're talking about the continuous setting. So if you search for geometric set covering with unit disks in the continuous setting. So continuous means you have the liberty to cover the points while placing the unit circles anywhere on the plane. So you are not constrained to pick unit circles from a set of given unit circles. So when the set of unit circles from which you have to pick is also given as part of the input, that is the discrete scenario, discrete.
Okay.
So Yeah. So this is a very elegant solution. So you can find a constant approximation. And the solution, I warn you, is slightly complicated, but the solution is elegant. And if you understand the solution, then you'll be wow. So let's look at it step by step. So our first target is to solve a simpler problem. So this problem is like a behemoth. So many points, so many points means around the city, you have to make a decision. So you say that, okay, this is such a large city and there are so many point locations that I have to cover. Why don't I try and solve it within, let us say, 100 cross 100 meters? So here in this case, for the sake of this problem, because the radius is 1 and the diameter is 2, I am saying that, okay, let us focus on a 3 cross 3 square. That is what I'm going to call a grid cell. So here is a 3 cross 3 square, which is what I'm going to call a grid cell for the for reasons that will become clear in a while. And I said that once I put this square on the plane, which is 3 units in length and 3 units in breadth, then I focus only on covering the points that lie within the grid cell. Okay. So in this case, this point to the left and these 2 points to the right are outside the grid cell. So I say that I am not worried about covering these points. Let us only worry about points within the 3 cross 3 grid cell. So what can we do? This problem is polynomial time solving. And this is exactly what we saw in the second part of yesterday's discussion, that within a 3 cross 3 grid cell, how to find the minimum number of unit circles covering the points in polynomial time. So any of you were there in that session? So I think that none of you were there. Nandana, were you there? Okay, so I'll assume that none of you were there in that session. But you must believe me that it is a fact that if you constrain the input to be points lying within a 3 cross 3 grid cell, then it is possible to find the minimum number of circles to cover these points within polynomial time. Okay. So once I upload the video, you can look at the solution. Okay. So here is the solution. So this is one circle and this is the other circle. And we had seen yesterday that the solutions are taken from a candidate set of solutions. So what are the candidate solutions? So either the circle has to pass through 2 points, and otherwise the circle has to pass through only 1 point, and that 1 point is the top point of the circle. So we're only going to focus on these kind of candidates, because if we do so, then only we can solve this problem in polynomial time. If you did not understand this, then just look at this picture and appreciate that these 2 circles cover all the 4 points within this 3 cross 3 grid cell. And one circle is such that a point is at its top, and the other circle is such that 2 points are at its perimeter. So far, so good. Any questions? If there are no questions, so with this algorithm at hand, I am going to design the algorithm for the entire problem when all the points on the plane are given to me. Okay. So we solve the original problem by solving many simpler subproblems. So first is I lay down a grid of this sort on the city, on the set of points. So all the input points are lying within the outer boundary of this grid. Now, this grid is composed of many 3x3 grid cells. So every grid cell is 3x3. So this is 3x3, this is 3x3. Think of it as a chessboard, where every cell of the chessboard has dimension 3x3. Okay. So we know how to find the minimum cover for 3x3 grid cells. What is minimum cover? Minimum number of circles to cover the points within a specified 3x3 grid cell. That is known to me. Okay, so what I'm going to do is for every such grid cell, where maybe some of the grid cells do not have input points at all, we don't have to worry about empty grid cells. But if there is a non-empty grid cell, for that grid cell, I will apply that algorithm that we have seen yesterday, and we will find the minimum cover. What is the next step to do?
We need to slide this. We need to slide this grid so as to cover all the points.
The sliding will come later, but once we have once we have solved within each of the grid cells, then what is the next thing to do for getting a solution for the entire set of points?
Maybe we take the union over all the smaller grid cells.
Correct. So we have already solved within each subproblem, within each grid cell. Now, to get the solution to the original problem, we have to merge the solutions to the simpler subproblems. Then I have a guarantee that all the points are covered. So to ensure that all the points are covered, I have to take the union of all the solutions, and then I can output the union. Right? So far, so good. Okay, so the union of such covers is definitely a feasible solution, because for every non-empty grid cell, I have a cover. So none of the points can remain uncovered. So every point is covered. That is guaranteed. Okay. So I have been able to produce a set of circles of radius 1 that cover all the points of my input. But then the question is, how good is this solution? We know that we cannot hope to solve it optimally. Then the question is, what is the approximation factor that we have achieved? Include any thoughts? This is not very difficult to see. So the question I'm asking is, let me write it down. It's difficult to really do this thing. That in the worst case, how far off can I be from the optimum? I'll just say WC. In the worst case, our solution. So let us say we have reported 10 circles. This could be less than equal to how many times OPT. So OPT is the optimal solution. So my question is, if I have run this algorithm and I have produced a set of circles, then when I compare it with the minimum number of circles required, then how far off am I? Give it a thought for a minute, and it will become clear. Let me give you some hint. So let us say that the optimal solution was only one circle, like this. So there are some points that this optimal solution has covered, and there were no other points in the input. So these are the points that we had. And the optimal solution is only one circle of radius 1. So you know that the grid cell width is 3 cross 3, and the diameter of the this is looking like a bigger circle. I have to make the circle even smaller so that the circle becomes of diameter 2. Let's erase this. Let's make a smaller circle. So diameter 2 circle, maybe something like this. So now we can see how far off we are from the optimal. Oh, Nathan has responded. Yes, I didn't see a response. Okay. If you cannot see, then observe that we are going to solve each of the grid cells separately. We are oblivious to the set of points that are lying outside one grid cell. So in this case, how many grid cells shall we solve? How many simpler problems do we have?
4.
Correct. There are 4 non-empty grid cells. So we have 4 subproblems to solve. Now in each of the subproblems, we can output, we can be unlucky and we can output one circle each. Because we are oblivious to the surroundings. We are ignoring the fact that there are points which are close by in adjacent grid cells, which could be covered using one circle only. We are oblivious to this fact. We are ignoring this fact. So therefore, we might have ended up choosing 4 circles because we are taking the union of the solutions of individual simpler problems. Whereas only one circle was sufficient. OPT was only 1. But we could have taken 4. Then what is the approximation factor we are getting?
It's 4, it seems.
Yes. So it could be as far as so we know for a fact that from this example, we are at least 4 factor off, maybe more, but at least 4 factor off. So can we do better? That is the question, and that is what Mr. Goyal was saying, that some shifting strategy will help. So what is the shifting strategy? So observe this bottom left grid cell. Okay. So I have divided this bottom left grid cell using these two horizontal lines and two vertical lines. So let us say that this bottom boundary of the grid is the x-axis. So then this line is y equals 1. This line is y equals 2. This line is x equals 1. And this line is x equals 2. Okay. So now I have this grid cell, 3 cross 3 grid cell divided into a chessboard. And the vertices are integral. The vertices of the intersection points of these divider lines are integral. Okay. So now you have solved the problem. You have solved the problem and you have produced an output for this grid cell, for this grid position. Now it is possible to shift this grid to one of the, let us say, I shift this grid 1 unit upwards. So if I shift this grid 1 unit upwards, then the bottom left corner of the grid will lie at this point, which is according to our coordinate system, x equals 0, y equals 1. So 0, 1. At 0, 1, it can lie. Another possible shift is I shift rightwards 1 unit. Then the grid cell bottom left corner will lie here at 1, 0. So depending on how much shift we have given, we can give 1 unit shift to the right, 2 units shift to the right, 3 units shift to the right. Sorry, if we give 3 units. So what happens when we give 3 unit shift to the right? We get the same grid. So to think of the grid as infinite. We're just showing the small part of the grid. The grid is infinite. The grid is laid on the plane. So if we shift by 3 units to the right, then we get the same grid, isn't it? Is it clear that if the shifting is with 3 units to the right, then the same grid will be obtained?
Just a doubt. These are not just 4 lines, right? So it covers the whole thing at a time, or just it does cover just the lower left square.
I don't understand. Let's
What I wanted to ask was, is it just 4 lines we are considering, or
yes, 4 infinite lines.
okay?
So I'm just saying that, okay, if so, consider this bottom left corner of the grid. So let us say this is the bottom left corner of the grid. Let us say this is the origin as per our coordinate system. This is 0, 0. So I'm saying that forget these lines. I'm saying that you shift this grid 1 unit. Then the tiling of the plane changes because they have shifted by 1 unit. But you have shifted by 2 units, then also the tiling will change. But if you have shifted by 3 units, then you obtain the same tiling. Are you not getting this? Let's do one thing. Let's get outside of this view. So consider this grid. So this grid is infinite. So I'm saying that if I shift it slightly, then we have a different tiling pattern. So earlier that there was a different tiling. So consider this is the floor of your this is the floor of the room where you were seated. Now, if the grid was here, then we have a specific tiling. It is shifted by 1 unit. We have a different tiling. Shifted by 2 units, we have a different tiling. But if we shift by 3 units, then we get the same tiling pattern. That's what I'm saying. Is it fine? Similarly, if we shift 1 unit to the right, we have a different tiling. We shift 2 units to the right, we have a different tiling. We shift 3 units to the top. Am I saying right? Okay. Top 1 unit difference, top 2 unit different, top 3 unit same. So there are 9 possible shifts. There are 9 possible shifts. So each shift will give you a different corner, a distinct corner of the grid. So let us say the original is the bottom left corner is at 0, 0. What is the coordinate of the bottom left corner? So it could be 0, 0, like the original orientation. You shift 1 unit to the right, it becomes 1, 0. 2 units to the right, 2, 0. But you cannot do 3, 0. Can you? Because if you do 3, 0, you are back to the same configuration. But you can shift 1 unit to the top. Then where is the bottom left corner? If you shift 1 unit to the top.
0, 1.
Yes. Yes. Now you are with me. You shift 2 units to the top, you are at 0, 2. But you cannot shift 3 units to the top. Because if you are shifting 3 units to the top, then you are back to the same configuration. But you can shift 1 unit to the right and 1 unit to the top, and the bottom left corner could be at 1, 1. Similarly, 1 to the right and 2 to the top. Again, 2 to the right, 1 to the top. 2 to the right and 2 to the top. Can you do anything else? There are 9 different shifts, integral shifts that you can perform. Okay, so we repeat the algorithm for all the these 9 distinct integral shifts of the grid. So for all these 9 different, so what can happen is, so we are interested in solving only within the grid cell. So that problem which we had, so that picture that I have shown you, that we can go wrong if we are oblivious to. So for example, if there's a point here, means very near to one of the corners, one of the vertices of the grid cell. Then for this shift, for the present shift, we may take 4 circles and say that, okay, solution is 4. But for if you shift, if you bring the grid cell here, I mean, if you bring the corner, bottom left corner of the grid cell here, then what happens? Then all these 4 points lie within one grid cell. If you give a 2, 2 shift and the bottom left corner of the grid cell comes here, then this should be pointed again. Then because of the shift, this grid cell now also shifts diagonally towards the northeast direction. And then this grid cell will be here. And will contain all these 4 points, and these 4 points now we can solve at one go within the grid cell. So what we will do is we'll return the minimum coordinated solution out of these 9 distinct positions of the grid. Does it make sense? If you have any doubts, you can ask me.
I have one doubt.
Yes.
You have said that shifting 3 units to the right or to the top is equivalent to no shift. So why
Yes.
are you considering the initial position as a shift, like 0, 0? If there is no shift,
No,
or
so
we
I am
shift.
so yes, so 0, 0 and 3, 3 are same. That's what I'm saying. I'm saying 0, 0 is a distinct position of the grid. So how many distinct positions of the grids are there? So let me write it differently. So let me say that repeat the algorithm for all 9 distinct integral positioning of the grid. Now you are happy?
Yes.
So you are right, there are 8 different shifts, but the initial position is corresponding to no shift. All good? Okay, so now we know what we have done. So now let's look at how good is the solution. Let's move to the whiteboard. So connecting my iPad. So you can see this. Hello. Okay. Are you able to see the whiteboard?
Yes.
Okay, so now we're going to analyze. So we have seen that, okay, if you do not do the shift, then you have a 4 approximation. Now we will say that if you do this 9 different shifts, as Gustav has pointed out, there are 9 different positions. There are 9 positions of the 3x3 grid on the plane. So if you solve 9 if you run your algorithm 9 different times, so you have 9 different solutions. So out of these 9 different solutions, you are returning the minimum cardinality solution. Okay. Now I want to argue that this is a better than Ford approximation. In fact, it is a much better than Ford approximation. And I have given you the intuition why this would be the case. Now let's look at this. So let us say this is one of the potential circles that you have output. So circle has radius 2. Sorry, circle has radius 1. So diameter of circle is 2. And you're looking at a 3x3 grid cell. So this is 3 units breadth and 3 units length. So this is a 3x3 grid cell. And this is a circle with a diameter 2. Okay. So now I say that consider an optimal solution. Okay. So the optimal solution, if you are lucky, and the optimal solution is such that none of the circles in the optimal solution, I'll say none of the OPT circles intersect the grid boundary. Then you also produce an optimal solution. So you have fixed one grid position. And now we are arguing that I'm saying that if OPT is such that none of the OPT circles intersect the grid boundary, then our algorithm also outputs optimal solution. So suppose every grid cell is like this. For every grid cell, you see that okay, either there is a unit circle like this, content. So nobody has shown you the optimal, but if it is so that if by magic you know what is the optimal, then you see that every optimal circle is contained within grid cells, not outside the 3x3 grid. Every optimal circle is contained within grid cells. There is no such spanning kind of circle that spans 2 grid cells. So let me grid boundary, I will make it slightly larger so that it. So this is the grid boundary. So is this easy to see? This is very important observation because from this observation only we will show that our approximation ratio is much better than 4. See, if you have laid down the grid and then you look inside every grid cell. So you have to solve the subproblem within the grid cell, that is your algorithm. And you have points within the grid cell. And you know how to solve the grid cell problem optimally. So if all the optimal circles are contained within the grid cell, then the the circles required to cover this grid subproblem are also within the grid cell. So such a circle does not exist. So such a solution where all the circles are within the grid cell, that is at most, that is also one candidate solution. So that is a feasible solution, and you know how to solve the grid subproblem optimally. So you have not used any more than the OPT number of circles in your solution. Let us introduce some notation, then it will be clearer. So let us define by OPT sub alpha, which is a subset of OPT. That means those circles. So let us say alpha is a grid cell. OPT alpha, which is a subset of OPT, as the set of circles in OPT that cover the points within a grid cell, a 3x3 grid cell. Let me write it down, 3x3. That covers circle that cover the points within 3x3 grid cell alpha. So let us say this guy, this 3x3 grid cell, we name it alpha. Then OPT alpha are those circles in OPT that are responsible for covering the points within this grid cell alpha. Fine. So this is the notation. Let us say when you solved the problem, you reported sol alpha. Sol alpha be the solution that you reported, that our algorithm reported for grid cell alpha. So we have solved it optimally. That we have seen yesterday how to do. Then sol alpha cannot be more than OPT alpha. This is the crux. Because we have an optimal algorithm within grid cell. So far, so good. But when will the problem occur? The problem will occur when you will look at the optimal solution and you will see that across grid cells there are circles. So this circle is spanning this grid cell, this grid cell, this grid cell, this grid cell, 4 grid cells. So this grid cell has neighbors. So this is one neighbor, right neighbor. This is northeast neighbor. This is north neighbor. So if there is a circle in the optimal which is spanning multiple grid cells, then you may be losing. Then you may be counting more than necessary. Like we have seen in this from the picture some slides ago. But how to quantify that? How much extra are we counting? So we have to quantify the extra counting. Okay. So we have to quantify the additional counting. Are you with me? If you're not with me, we can repeat it. If you're not with me, then there is no point moving forward. Or we can also drop it. We can look at feasibility questions.
You can repeat the last argument.
Okay. There is no point for me speaking and you not understand. So what I'm saying that you have overlaid this grid. You have overlaid this grid on the plane. Okay, so now you have a tiling of the plane. Now each piece, each tile is a grid cell of dimension 3 cross 3. Now consider an optimal solution. So let us say now I'm going to do the tiling. Let's say I'm looking at the tiling. We have done the tiling. So every tile is 3 cross 3. Every tile is 3 cross 3. Now somebody magically gives you the optimal solution. And you are surprised to see that all the circles in the optimal solution are such that they do not intersect the grid cell boundary. Surprisingly, you see that. You understand? This has happened. Now I'm saying if this has happened, then your algorithm that you solve within every grid cell and take the union of all the solutions in the grid cells, that is also going to report the optimal solution. That is the claim I'm making. If this is the case. Because within the grid cell, whatever points are there, for that you know an optimal solution. So your solution for a grid cell alpha is the best. It cannot be poorer than anything. So even OPT sub alpha, which is that portion of OPT for the grid cell alpha, that is worse than your solution. Give it a thought for a minute. This is without any shifting strategy. This is fixing one grid pattern. And then if such a thing happens, that the optimal is not intersecting any of the grid boundaries, then you cannot but help outputting the optimal. Is it still unclear? Then we can discuss it. Okay, fine. I think that I'm not making sense. So I do not know whether I should go forward. So we can show that it is going to give a better than 4 approximation. So let me just look at this way. So of the 9 different solutions that you have obtained, if you return the minimum cardinality solution, then instead of 4, you are going to get 9 plus 4 by 4 approximation. So that is 13 by 4 approximation. And that argument can be done only if you understand this. But I think that there is no response, so there is no point. Okay. So anyhow, let's move to the visibility questions, and if there is time tomorrow, maybe we will look at it. I'm going to look at the visibility questions, so I'm going to share the slides once again. So this is the complicated argument, as I told in the beginning itself. But if you understand it, is very elegant. I mean, first time you say it is not easy to understand. I also did not understand the first time. That is fine. Let's share the screen from the laptop again. Shall we take a break now, or we shall go through these feasibility problems?
We can take a break now.
Okay, fine. So let's take a break for 10 minutes, and 6:10 we can come back. It's 6 o'clock now. 6:10 we can come back.